One of the most groundbreaking games of the 8-bit era was Elite. Elite is a space trading game where the player makes money by trading and killing bad guys. Two things stand out with the design of this game. It's an open world and the 3D frame graphics. It's one of the first games not to have an ending. But for me it was the wow factor of the 3D spaceships flying around in combat. At the time, I've never seen anything like this before. I've always wanted to know how the 3D graphics were done. One day, trawling through the October 1990 copy of the Amstrad User magazine, I came across this article, 3D Fundamentals. It explains in simple terms how 3D rotations can be achieved by using some basic maths. It also includes some basic code that you can type out. And here it is running on the Amstrad. It's pretty slow, but the simple 3D objects do rotate in the X, Y, and Z axis. The challenge was accepted. I just had to figure out how to do this on the Z80 in assembly. I have my Tech 1F single board Z80 computer and a graphical LCD screen. It ended up being one of the more complicated pieces of code that I've ever written. So this is my graphical LCD screen. Its dimensions are 128 pixels across and 64 pixels down. There's a few variants of these floating around, but they all tend to have the same LCD hardware processor, the ST7920. So turning this screen around, it's branded as a 12864B. In fact, it's a QC12464B. Looking at the pin connections here, fairly standard for LCD screens, but there's a few extra pins. And one of the benefits of this screen, you can also communicate not only in parallel data, but also serial. When reading up about how this screen works, it has two components, a text and a graphic layer, where both layers can be shown at the same time. Also, when writing a pixel to the screen, you are required to give it two instructions, the X and the Y coordinate of where the pixel is, and then the data, which is 2 bytes long. And the 128 pixels across are separated by 7 double bytes. And for every 2 bytes that are sent to the screen, up to 16 pixels can be shown. Comparing this to a standard LCD screen, a 16 by 2, the pins are essentially all exactly the same, except for one extra pin which can either set serial or parallel communication. So let's see how we can fit this screen onto the tech computer. The graphical LCD has 20 connections. A standard 16 by 2 has only 16. But in total, there's actually only one extra pin. Let's have a look at the pin connections now and how we can connect this to the Z80. So the first pin is ground, VDD is 5 volts. The DI stands for data or instruction register. Data is high and instruction is low. Now I've connected that to A7, so I can choose the data or instruction at the same time as enabling the chip as well. RW is read and write. Are we reading from the LCD or writing to it? Typically we'll be writing, and that's just connected to the read line of the CPU, but inverted because read is active low, and on the interface it's active high. And E is enabled. This needs to be connected to the output port. Now I've chosen port 7, and port 7 is low, but E is active high, so we need to invert it. So with the combination of A7 and port 7, I can use port 07 as the instruction port, and if A7 is set, I can send information to the data register with port 87. The next 8 pins are straight out of the data bus, D0 to D7, and then we've got P and S. This is the extra pin that the other LCD or the small LCD screens don't have. This interface can also be used as a serial connection or parallel. So parallel is high or serial is low, so I've connected this to 5 volts because I'm just doing parallel at the moment. Then we have reset. This is just connected to the reset line of the CPU. This resets the screen, and the two LED power and ground. That's the backlight. I have noticed the backlight is very bright, so probably a resistor here to reduce the voltage will be better. I don't use the backlight. And then we've got 3 leftover pins. They're not connected to anything. VEE is just an output power. NC is you don't connect it. And over here, this is interesting contrast. Normally you would connect it to a 10K trim pot between ground and 5 volts. to modify the contrast. It actually has got auto contrast, saves you one extra component. Okay, let's plug this into the tech computer now. Here's the LCD screen plugged into my Tech 1F computer. On the Ultimate Expansion sandwich board, I can easily extract the pins from the CPU into this breadboard, into the inverter to the port and the read lines, and then onto the screen. So let's now turn it on and see what happens. Well, nothing. Wouldn't it be great if you can just get graphics working straight away? It's not so simple. But in order to get 3D objects rotating on this screen, I've got a few issues that I need to work out. Firstly, how do we actually draw a line between two straight points on the screen? It sounds simple, but with the Z80 we only have whole numbers and registers that are only 8 or 16 bytes. And I'm also pretty sure I need floating point numbers, so how do we actually do that on the Z80? Also, how on earth do you display a 3D pixel in 2D space, X and Y locations here? And lastly, what about just rotating objects around the screen? How is that done? So I am aware there's a bit of theory that's needed just to get something on the screen here. So bear with me and I'll go through some of the stuff that I had to figure out to get the 3D modeling working. Have you been dreaming of that electronic project and want to make it a reality? Just like my Ultimate Expansion board for the Tech 1F. Well, head over to PCBWay to make your dreams come true. PCBWay are the leading printed circuit board manufacturer. They make high-quality multi-layer boards with a 24-hour production time. Just enter the board dimensions and upload your Gerber file, and that's it. Once posted, a neat box will arrive with your well-packed goodies. Just look at the quality of this board. They also do PC board assembly, CNC machining, and 3D printing. You can even order user project boards directly from their website. For $5 off your first order, click on the link below. PCBWay, prototype the easy way. One way of drawing straight lines between 2 points on a screen which is effectively an integer screen, whole numbers only, I can utilize the Bresenham algorithm. This algorithm was developed in the 70s for plotters, and it's perfect for this LCD screen. So how do we draw a line between 2 points on an LCD screen? It seems pretty straightforward, but we've only got whole numbers when we're dealing with the Z80. Let's say we want to draw a straight line between 1, 1 and 6, 4 on this XY Cartesian plane. So how are we going to do that? And which pixels are we going to light up to draw that straight line? Well, we know the first 2 pixels because that's the start and the end. But what about in between? Now we know that on every iteration, X is going to move up by 1. So the question is, are we going to go up 1 or across 1? And this is where this algorithm looks at the midpoint between the 2 points and the rate of change. It works out which point has the least amount of difference between the actual line. So for the next point, we'll move across 1 and up 1. It's 2, 2. That's the closest square with the least amount of error to the gradient of this line. What about the next point? We move across. Are we going to move across 1 and keep the same Y, or move up 1, get the midpoint? In this case here, we're not going to increase Y, we'll just increase X. So the next point is 3, 2. And we move across 1 again. Are we going to go up or keep on the same Y? In this case, we'll go up. So 4, 3. Do the process again. This pixel here has the least amount of error, so we'll keep the same Y, 5, 3. And then we finish off with the last one, 6, 4. That's the basics of the Bresenham algorithm. And here is my implementation of the Bresenham line algorithm. This is the code in C, and I've just copied line by line and interpreted that into the Z80. The line draw just has an input, x0, y0, x1, y1, and a line will be drawn. I've got now the Bresenham algorithm loaded, and let's draw some lines. And here's just an example of 2 straight lines going from left to right and up and down. Pretty happy with the outcome there. So now I've got the line drawing. What about floating point numbers or fixed point numbers? How can I get that implemented on this Z80 machine? Let's have a look now. So I have a feeling with rotating 3D objects, I'll definitely need some floating point numbers. What is a floating point number? Well, it's basically a number that isn't a whole number. It has a decimal place, and some numbers after that decimal place. So how do we represent fraction of numbers or floating point numbers in the Z80? Because we've only got these registers 1 byte or 2 byte, and they're like whole numbers from 0 to FF. But we can use a similar concept that they use in other languages called float. How could we represent 15.65234375, some seemingly random number, using floats? Can we implement that on the Z80? And this number looks like this, as a 4 byte or 32-bit number, but it is broken down into 3 components. They are the sign, the exponent, and the mantissa. Exponent is basically to the power of. Mantissa is just a technical word for the numbers after the decimal point. So we can use these 4 bytes. You can see they've got 8 bits each. Perfect, that will fit well into the Z80 system. But how do we interpret these 4 bytes? Well, the sign is the first bit, and that's 0. The exponent is 82 hex, and the mantissa 7A, 70, and 00. What do we do with these numbers? So for the sign, we have -1 to the power of that number, which is 0. The exponent is 2 to the power of. 82 in hex is 130, and we minus 7f from it, because we've got to look at the midpoint of this number, because we might want negative exponents and positive. So 7f and 80 are the midpoint of an 8-bit number. So we'll always minus 127 from whatever the exponent is. And the mantissa, now this looks complicated, but it's actually not. We multiply the exponent by 1 plus, and then for every bit set, we add 2 to the power of, because this is of base 2, of -1, -2, because this is the fraction component of it. 2 to the power of -1 is 2 to the power of a half. So it's -1 plus -2, 2 to the power of -3, 2 to the power of -4. Then we skip over the 5th bit, because that's 0, 2 to the power of -6, and then we've got 9, 10, and 11. And we just add those numbers together, and that's how the mantissa section is interpreted. So what does it come to? Well, we got 1 here because the sign is 0. Anything to the power of 0 is 1, times 2 to the power of 3, times 1.9565, etc., which is the combination of these exponents here. And that comes down to our number that we're looking for. Now, this is way too complicated for what I need for this. I think I can do something a lot more simpler, but is there another way to handle floating point numbers or fraction of numbers in just an easy way to implement? Yes, there is. And that's a fixed point number. What's a fixed point number? Well, again, we're going to use the same fraction of a number that we want to use, 15.65234375. Would you believe me if I can represent this number up here with just 0FA7? But if I convert this to decimal, it comes down to 4007. So that's not correct. But it's how we view HL. If we view it in a slightly different way, let's say we do H.L. That brings our number to OF.A7. So we can use the H part as the integer and L part as the fraction. This is referred to as 8.8 notation. Now this is obviously limited to positive and minus 127, but for the numbers I'm looking for, it's going to be much smaller than that. So this will suit perfectly. So what's OF? Well, OF in decimal is 15. Great. What about A7? A7 is 167. Now remember, this is the fractional part, and there's 256 numbers that can fit into A7 from 0 to FF. So we divide it by 256, and we get this fraction number. Putting them together, you get our magic number of 15.65234375. And fixed point numbers will work perfectly for 3D rotations. So I use fixed point notation to represent the points for my 3D shapes. Represent -1, I use FF00, and 1 is represented as 0100. And here's an example of the cube data, where I draw in a line between 2 points. Here are the 2 points, point 1 and point 2, and their fixed point notation value. I also have the total number of 3D points and the default size. The next thing we need to work out is how do we convert a 3-dimensional point with X, Y, and Z components to a 2D picture. because the LCD is only 2 dimensions, vertically and horizontally. So in terms of visualization of X, Y, Z, we can see that the Y goes up and down, X goes left and right on the screen, and Z, well, I've got this 45-degree here, but just imagine it's going into the screen and back into your eye. That's the Z component. So here's an example of how we can use the Z component on a 2D plane. So just imagine there's a person. Now, how big is this person? Are they a few centimeters? Are they a few meters? You really can't tell unless I have something to compare it with. What about this person? Is that just a midget compared to the first person, or are they further away? If I make a vanishing point towards the second person, you can see now that these two people are probably around the same height, but one's just further away. And even though these two people are in 2 dimensions, the Z can be used to modify the X and Y value to make it bigger or smaller. But the question is, what's the rate of change between going from big to small or small to big? Is it linear? But realistically, when we see something in the distance, it doesn't just disappear to nothing. It tends to slowly shrink. So it's more like it's logarithmic. And we can use this simple formula of 2 to the power of Z to modify the X and Y values. So how does this work in a more practical example? We have 4 points here which form a square, and each of these 4 points are 3D points. But what about the Z? So if we assume Z is 0 in this case, we just multiply the X and the Y values by 2 to the power of Z, or 0. And 2 to the power of 0 is 1. Having Z as 0 is essentially the center point between being close to you or further away. Let's now make Z equals 1, so something that is closer to us. Because it's 2 to the power of 1, it's actually 2 times bigger. What about Z equals minus 1, further away from us? Well, 2 to the negative 1 is a half, so it does look smaller, but not at the same rate. 2 to the power of Z works well for what I want, provided that the points are all between 1 and negative 1. And here's a picture of a cube that's been converted from 3D space to 2D space using the Z factor as its distance or depth factor. Now here the vanishing point is right in the middle of the screen, and would you believe that little square in the middle is the same size as the big square on the outside. It just happens to be further away, or the Z in the negative, and it's shrunk the square. Then joining the lines together, I've got those angled lines towards the back of the cube. I still haven't got this rotating yet, so let's work out how we can rotate this cube. The last thing we need to work out are 3D rotations, and surprisingly, this is one of the easiest things to implement. We're going to utilize the rotation matrix. What is the rotation matrix? And this is what it looks like. We've got X rotation, Y rotation, and Z rotation. Now this might seem way overwhelming, but it's actually quite simple to use. So for instance, let's just look at the X rotation because they all implement it in the same way. If I put some labels next to it, it makes it a bit easier to understand. So in the columns, you've got X, Y, and Z values. This is pertaining to the original values of X, Y, and Z for that particular point. And in the rows, we've got the next value. So the new X, the new Y, and the new Z. So when we rotate around the X axis, what's the new value of X? The new value of X is just X times 1 plus Y times 0 plus Z times 0. Anything multiplied by 0 is 0, so we can ignore any zeros. And X times 1 is just X. So when we do rotate around the X axis, that particular point doesn't change. And that makes sense in terms of that's why we're rotating around it. What about the new value of Y? Well, this will change. It's the old value of Y times cos of theta, of the angle of change, plus Z times sine theta. And the new value of Z is the value of Y times negative sine theta, and plus Z times cos of theta. So we only need to implement 2 equations, new Y and new Z. And to make things even more easier for the implementation is to just hard code the value of theta. And I've done that by making theta, or the rate of change, as 10 degrees or 0.1745 radians. So finally, we can now implement rotations of these 3D objects. Let's start rotating. Alright, now the code's been loaded to rotate the cube. Let's rotate it by the X-axis. Here we go. And that looks pretty good actually. You can see it flipping around in the forward. Now every rotation is at 10 degrees by default. What about the y-axis? Yep, that's spinning around the y-axis, which is up and down, so it's rotating around the vertical axis. And lastly, the z-axis, rotating, inwards into the screen and back out again to where you're looking. That looks pretty good. All three rotations are working. The shape is still maintaining its dimensions. There you go. I finally have done it. My 3D rotating is working on the LCD screen. It's kind of interesting. You've got the line drawing working here, and you got the rotating graphics, but in order to actually get the lines to work and the graphics to work and this LCD to work, I've had to write a graphics library just for this LCD screen, Z80 based, purely Z80. I've seen a lot of different code out there to interface with this LCD screen, but it's mostly Arduino based. This is my Z80 implementation. In order to get something useful on the screen, I've had to implement a graphics library for the Graphical LCD. I couldn't find any native Z80 libraries that interface with this screen. A lot of Arduino code, but not on the Z80. So this code's very portable. You can use it on any Z80 microprocessor. Just a few setups. Here is the port values to send data to the instruction register and the data register. That might change depending on your setup, and the particular delay needed between commands sent to the screen. And it also has a set of functions that you can use to clear the screen, set particular modes, graphic or text mode, draw boxes, draw circles, draw line, draw filled circles, and strings and characters to the screen. It actually uses a graphics buffer to store all the pixel values, and once those values are ready to go, you can then just write to the screen by using plot to LCD. Let's have a look at some of these functions in action. For my 3D rotation program, I've created a menu which uses most of the graphic routines that the graphic library has. Let's step through it. To display text on the screen at a particular row, there's only 4 rows. You select the row and then call print string. The next line is the string to be printed, terminated with the 0. And here's the text on the screen. The font is 8 by 16 and you can only use the 4 rows. There is an inverse routine, but it's a bit messy with this screen because how the hardware is implemented. To get around that, I just print a filled box behind the text and it inverts the text. So I set the graphics mode because the next instruction will be graphics. I fill out B, C, and DE with the XY coordinates and call fill box. There's a filled shape behind the text, and if the graphics is being overlaid by the text gets inverted. What about hollow boxes? Same input, x1, y1, x0, y0, x1, y1, and draw an outline box by calling draw box between those 2 points. And here's a rectangle, lined rectangle. What about printing characters at certain points on the screen? I switch to text mode, load the data to be printed into HL, and then I use BC, where B is the column and C is the row. And then I just call print chars. What's menu data? Menu data is just, again, a string terminated with 0. What about some more text there? Text at certain locations. Drawing lines using the Bresenham Line algorithm. I set back to graphics mode, and then the 2 points in B, C, and DE, and I call draw line. Let's now put some individual lines using the Bresenham Line algorithm. Looking good. What about drawing circles? You load BC with the midpoint of X and Y, E as the radius in pixels, and call draw circle. Some hollow circles. Also have a fill circle function too. Fill circle is actually calling the draw circle, but at every iteration increasing the radius. Filled circles, and I kind of like how the filling does look like the old BASIC code when you do graphics in BASIC. There are some gaps there. You can also draw individual pixels to the screen with an X and Y coordinate. I have the draw pixel routine that draws a pixel at BC, where B is X and C is Y. But to make it a bit more interesting, I load the data from the pixel data address, and this routine just loops through the data until it finishes and draws a pixel at that point. What's pixel data? And here it is here. So this will draw the letter T on the screen. And I've just got the X coordinate and the Y coordinate. And here's a graphics picture here. And I'm just setting the pixels here, individual pixels, to write the word tech. All right, and as you can see, I've got some more 3D shapes here. Let's have a look at them. Pyramid. Rotate around the X, Y, and Z. And triangle here. This is the triangle based on the Amstrad magazine code. And Cobra, what's that? Is that Commander Jameson's Cobra Mark II? Yes, it is. And finally, I was able to implement a spaceship on the Elite game and make it kind of look like Elite. And I can do the rotations around the X, Y, and Z axis. And it's looking pretty good. And finally, just for a bit of fun, back in 1985, Mad Magazine had a special computer section edition where you can type in some code to your 8-bit computer and produce the face of Alfred E. Newman. And this is the code. You can use it on your Apple or Commodore or Atari. It even has some interesting notes for the Apple user. After you finish entering the program, be sure to save it before calling it for a printout or you're screwed. You can try this on a Mac, but it won't work, only Apple II. How the program works, it's just a set of two XY points and a line is drawn between them. Hey, that will work perfectly on this program. So I was able to implement this MAD code using a C++ gaming engine. This is what it looks like. Even the 1980s basic slow style of drawing the lines. I got the data from this program. I converted to 128 by 64 LCD screen. And finally, here's Alfred E. Newman. So I'd like to thank you for watching this video. All the code is online, so you can download and modify and create your own amazing graphics and examples and pictures on the LCD screen, all native to the Z80. And on that note, what me worry. See you next time.